Alright gamers, welcome back to another Vector Spaces video. Today we're continuing with, I might be miles away from my microphone actually. So it could be too close, let's experiment it with a tiny bit and then, sorry, we'll get back to it. I think that'll be alright, I can mix it in post and hope for the best. Okay, yeah, because I was looking at the previous videos and like the volume goes up and down, so I'll try and keep like a steady dynamic / loudness of voice. Okay, so chapter 3, we're on Subspaces. Last episode we went through all the theory. There's about 7 items of theory, and as promised, we're now going to do some practice questions on these ideas. Hopefully, I can do this for all the chapters. There's only going to be about 6 chapters, maybe 7, and some of the earlier chapters are really small as well, so it should be possible. Hopefully, like all done within the next 3 or 4 weeks, but that might be quite ambitious. So just see what I can get done. So I think the best way to go about these ones, we've got 3 today. I think there's only about 3 in chapter 3. I could probably make a few quick more questions if people wanted that, but I don't know if I'll get many requests for that, so we'll just do these ones. And I think the best way to do it is, assuming you've probably just watched the previous episode, or maybe you go back and watch that if this isn't, unless you remember all of this, in which case all is good. I think the best thing to do is just try these questions yourself, and then maybe spend about 5-10 minute stops on each one. Although to be fair, they're all similar, so maybe if like you're struggling with the first one, then maybe skip and watch me do the first one, and then try the other 2 or something. But yeah, so these are the questions. Hopefully my handwriting is just about readable. This video, I think I should be exporting in 1080p, I hope. So hopefully like you can read stuff, but if not, sorry about that. This one you just got x1, x2, x3, x4 of the set of real 4, where all of the coordinates are of the set of integers. This one, the equation is x1 plus 2x2 plus 3x3 plus 2x4 plus x5 equals 1. And this is in a real 5. And this one, real cubed, we've got 3x1 minus x2 plus 2x3 equals 0. And I'll give you a few seconds to pause the video. Okay, assuming you have, let's go on to the first one. Alright, so right off the bat, if you recall, so the question, I didn't read the questions here, I was hoping you could read that. It's just, is U a subspace of V, and then prove the result. There are probably more like precise ways to write this, but I thought it was pretty clear what you're going to do. You're going to find out whether it is or not, and then you're going to do a proof. You could either be proving that it is a subspace or disproving if you think it's not a subspace. So for this one, I guess the first thing we should do is figure out, is this a subspace of V? So the first test is U a subset of V? And as we see, because we've defined it so that every element of U is in real 4, which is V, which is also real to the 4, then we know that, I'll try and make that really clear, it's curvy. We know that U is a subset of V, so it could be a vector space, but it might not be. The next test to try and figure out if it is or not is, if you remember from the chapter, if it is theorem 3.5, we have that U plus V, or lambda U is of U for all U of U. Yeah, so you take UV of U, and then you see, doing these operations, is it still within U? So I think the best way to go about these is you assume it's not a subspace. Like, always assume it's not, and then try your best to show that it's not. And if after like a few minutes you can't show that it's not, then assume it is. So this is very easy to accidentally go, oh, let's take the vector 1, 2, 3, 5 of this set U. So we've got this vector in U because that's how we've defined it, such that they're all integers, and go, well, if I multiply it by 3, then we have, this will obviously, whatever it is, will have 4 integers, so it's still in U. And we might go, oh, well, if we have 1, 0, 1, 2 maybe, plus 3, 4, 5, 3, then again, we've got integer results, so yes, it's in. So it's very easy to accidentally just do this, that, and go, oh yeah, it's a subspace, but it's not a subspace. And the reason is you got to be like as maverick as possible. There's no reason why this multiplier has to be an integer. That's just not what the definition is. Lambda can be of anything of the reals because we're working with a real vector space. I've kind of omitted this information here actually. I maybe should put that. This is kind of implicit, and this happens sometimes with higher level algebra and also just vector spaces. But this is a field over R. So therefore, our multiplier here could be any real number. So we're going to go straight into the disproof. So for our solution, this is our rough working. For our solution, we start it here. So we've identified that U is a subset of V. So it might have been a subspace, but in actuality, we're now going to say, but actually, we have that U is not a subspace of V. And then we may be right. We prove this to signpost to the reader what's going on. So, how do we go about the proof? We simply look at remark 3.7 we made last time, and we need one of these two counterexamples. As discussed, we're going to do this counterexample. I'm just going to copy that theory. I'm going to try and copy that theory. I'm going to copy that theory. I always post in the dumbest of places. Oh no, actually that's alright. No, it's not. We're on example 3.10. We're doing 3.8 first. So drag this up. So this is the theory we're going to use. So all we need to do is choose some U of U, then choose some lambda, and show that for that lambda and U, it's not of the set U, and then we conclude our proof. What was the theorem that backed this up? Oh, I think we just appeal to theorem 3.5 directly after we... So we're using remark 3.7, but we're going to appeal to theorem 3.5 for our conclusion. Okay. Because a remark isn't a theorem, and we have to use a theorem to be logically rigorous in our proof. So we prove this. We just say let U equal anything really, maybe 1, 2, 1, 1. Choose any numbers you like as long as they're integers is important because that's our definition of U. So this is of U because they're all integers. And then we'll say let's lambda equal, I don't know, what we're feeling. I think 1.5 is fairly clear. I want to like make the numbers not too hard to calculate, I guess. I probably thought about that a bit too long. You can be much quicker. Well, you should be a lot quicker. I'm sorry about that. Okay, and then we can say we see that lambda U equals 1.5. 1.5 times 2. That 1.5 is 3 over 2 as a fraction. So you multiply that by 2, you get 3. 1.5, 1.5. We say it's not of the set U. Do a quick bit why, because because 1.5 is not of the set of integers, implies by theorem 3.5 U not sub. Let's make it pointy. It's weird, on paper and pencil I always don't struggle with making it pointy, but for some reason with a drawing tablet it likes squiggles, you know. We'll get there. Hopefully my dynamics have been good with the mic as well, I'm not sure. I think it's been better than it has been, but I need to remember to like use my loudness of voice. Let me just write a square and be like, our proof is done, yo. Okay, let's move on to the next example. Hopefully you got that, if not, try the next two. If not, let's jump into them. So this simply used the idea of being rebellious, but there's another trick you can use. So one is to be rebellious, I think is a good way to think about these questions. And the other thing is there's a very simple trick. So exam setters, because this is like a linear algebra topic, tend to give you linear equations and the definitions. They don't have to, but they tend to. So one of the nice things about linear equations is one, a linear equation like this in the form oh, and by the way, I didn't say this before, but these videos are designed to be a bit less formal than the main theory ones. Like the first episode of each chapter I'm going to try and be more formal, as these it's like I can kind of do whatever, it's more relaxed and more let's just solve some problems, you know. But then again, I kind of like being formal with presentations, so maybe there is literally no difference in in style and quality of said videos. I don't know. Well, I don't know about quality, but we'll see. Okay, so we have this linear equation. And one nice thing about linear equations is, what is happening? OneNote being kind of buggy. It's still better than like remarkable. There might be another note taking app that's better. I've not found it yet though. Okay, so we've got lambda 1, anything of the form lambda 2, x2. Oh, this isn't this form. This is just, maybe I should do this over here to make it clear. This is just general linear equations theory. So we've got lambda 1, x1, where this is just some scalar multiple. Lambda 2, x2. Plus no, not xn, lambda n xn. For goodness sake. There we go. Xn equals d, where d is scalar multiple and so are these lambdas. Then we know this is going to be some hyperplane. In particular, it's going to be an n-1 dimensional one. So examples of hyperplanes are you've got a line as a hyperplane, you have a 2D infinite sheet of paper as a hyperplane, and in higher dimensions, like in fourth dimension, a cube that stretches infinitely in every single dimension is also a hyperplane. So it's generally just the general infinitely stretching geometric objects. But if you can't process that, you don't need to. All you need to know is that one particular property of these hyperplanes is they'll either contain the origin, given by 0 equals 0, 0, n times, because we're in n-dimensional space. No, yes we are, yeah, we're in n-dimensional space. So it'll either contain the origin or it won't, and it just so happens, I did a quick proof on my second channel, I'll leave it on the top, not top line, just under like the main introduction and the description, like the next line will be a link to my proof on this. It's got no views currently, which is very exciting, but I don't know if anyone cares about the proof of this, but turns out if d equals 0, then the hyperplane contains the origin, and if it's not 0, it doesn't contain the origin. That's a lot of dense for it, it probably doesn't matter. In this case, all we need to know is that this is a hyperplane. It just so happens by the theory this is a 4-dimensional hyperplane in 5-dimensional space, but you don't necessarily need to know that, you just need to know this thing will either contain the origin or it won't contain the origin. That's entirely dependent on whether this is 0 or not. So because it's not 0, then this thing doesn't contain the origin, therefore we know U can't be a vector space. So maybe I'll do that as rough working. So for linear equals 1, we see 1 not equal to 0, so we have the 0 vector is not of the set U. Therefore we know that U is not going to be a subspace of V, but this isn't really a formal proof unless you copy and paste the proof I did on my second channel every time, because you would need to justify this result, but you can use it to know ahead of time what the answer is, and then we can simply use the theory we looked at last time to then rigorously justify that it's not. So we know it's not, so again we're just going to use remark 3.7, appeal to theorem 3.5, and cook together an answer in a few seconds. So let's do that. So one easy way is just choose lambda equals 0, and then multiply 0 by any vector of U. You're going to get the 0 vector, which isn't in U, and therefore we will be able to prove that U is not a subspace of V. So let's formally write our answer now. Spent a bit. I think the geometry's fun. I think geometry's cool. Not everyone does. It's like I heard one time someone was saying how uncool it was that people talked about their favourite shape, and I was like, you know what? If they want to do that, you gotta let them live their right life, right? Okay, let's do some math, I guess. Okay, what's happening? No, it is so that U is not a subspace of V. Very dramatic. We prove this. To be honest, I probably shouldn't write yo at the start of an exam style question, but this isn't an exam, this is just some weird guy on YouTube making maths videos, you know, we out here. Okay, so we prove this, so how do we do that? Well, it's the same as before, so I'm not going to go for it any slower than I need to. Let's just say let U equal literally anything. What's fun? Oh, I know, 69, 1, 1, 1, 1 of the set of... Oh, no, we can't just choose any odd numbers. We're not choosing any vector of R5, we're choosing anything of U, which is a bit harder to do because now we've got this. How do we do that, actually? I know. We can just set it to 1, so x1, we'll have 1 on one side and we'll have 1 on the other side by setting every other variable to 0. So 1, 2, 3, 4 zeros, and then we have this is of the set U. You can check that if you want, but just because it satisfies this equation by construction when we have this. Let's say let lambda equal 0, and this is why there's only really 3 examples. Like, it gets very laborious very quickly, but we'll just rush through these examples and then you get some examples to go into your plates of mathematical knowledge. Okay, so we've got lambda of equals 0 of the reals. We see lambda U equals 0, 0, 0, 0, 0. So then how do we apply to this? Oh, I can just say if, no, we'll say let vector A equal that. If A of the set U then satisfies. And as annoying as it is, you would have to copy this out, but because I'm working digitally, we can just copy and paste because we like that. Satisfies this. But for A, we see, what do we see? We see 0 plus 2 lots of 0 plus 3 lots of 0 plus 2 lots of 0. You knew maths was going to be exciting, right, guys? Oh my gosh, pure maths be like equals 0, not equal to 1, implies that A equals lambda u is not of the set U, and this implies by theorem, no, not 3.5, U not, sorry, pointy, U is not a subspace of V. Alright. And one more to go. I hope you're very excited for this. Alright, so we continue. So before we just did example 3.9, now we move on to this one. So, as discussed, whenever we have a linear equation, which in this example we have as well, then it's a hyperplane, and as discussed as well, and it's in this form, with this value here being d we looked at before. We said when this was 0, that this entire geometric plane described by u, we have that the 0 of the vector belongs to u, and this gives us, right off the bat, because v is just r cubed, we can immediately just see that u will be a subspace of v, which means we can jump straight to using lemma 3.6 that we discussed before to prove this result. So let's first we'll copy the theory from lemma 3.6, which just extends theorem 3.5, the fundamental one about this whole idea. Well, it's more that theorem 3.5 builds into theorem 3.6 or lemma 3.7, but these are the ones you actually would use. Anyway, I'm going to copy all the theory just so we... No, I'm not. I'm just going to copy this, but this is the only important bit. So in math, sometimes this other bit here. Oh. So sometimes this bit over here, this section here is just like for formality, but here it's actually really important that critically this bit we need to be true for every single combination of u, v of u, and also with the combinations of lambda of the field, which in this case is equal to the set of reals. Sorry if I went through that a little too quickly, I just don't want to make it too long, you probably get the point by now. So it has to be for every u, v of u, and for every lambda of the reals. So the way you want to go about this, and you can get into a lot of trouble if you try and do it any other way, so as weird as this looks, this is like the way you want to do it. So first of all, we conclude that uv, no, I should probably write yes to be extra clear. Yes, u is subspace of v, and then we say that we are going to prove this. Alright, and how we're going to do that is we're going to start our proof by first of all saying let u equals A, B, C. Maybe with? That might be a better way to word it, but that seems clear enough to me. And then all we're going to do is we're just going to copy this equation but shove in A, B, and C, which looks ridiculous, but just go with this for a second. I'll try and convince you on this in a second. So essentially what we're doing is by setting up u this way, where A, B, and C are any reals, which we'll write in a second, but I want to do a few other things first. Because A, B, and C are any real numbers, and because we've said it's going to satisfy this, it must be of u by definition. And furthermore, we can choose A, B, and C to be any numbers such that this vector u will be any vector that belongs to u. If that didn't all click, you can just write this each time. But that's the sort of reasoning behind it. And it's just kind of like one of those maverick maths things where it's like, well, if we just copy the definition, it's guaranteed to be every u of u, which is weird, but that's the thing you can do. It's a pretty legit way to solve this question. But I did spot another way you can do this, which we'll discuss later on. So I'm going to write 3 star 1 here to remember to come back to this for anyone who's interested in like absurd ways of solving this question, because it's just kind of fun. Okay, so we've got D, E, F. We've got to be careful E because sometimes E can be 2.7-ish, but here it's obviously we're using it as any real variable. With again 3 minus, no, not 3. I had E on my mind. 3D minus E plus 2F equals 0. And then we'll write it here with A, B, C, D, E, F, set of reals. I'm sorry about the handwriting, but no one really cares, it's fine. Just want to zoom through this. Then there are probably other ways you could word this, maybe makes it clear, maybe not, but I think you could just get confused if you write too many symbols here. I think it's fine to just say then U and V are not V, of U. They are of V, but that's not the point. I guess, I mean, it's kind of implied because we've got R cubed here and here. Kind of you can see, I don't think you necessarily need it for marks all the time in exams, but you could say U is a subset of V. That wouldn't be wrong. Some point here, maybe here. We could write that if we wanted, but I don't think it's too important. Okay, so we've got these real numbers here. We've got U and V of U, and then we simply apply to lemma 3.6, which is that we have to have U plus lambda V as of U for all UV lambda. Oh, so then we should also say let lambda be any lambda of reals. Maybe we should write any here as well, to be clear. These aren't fixed values, these are variable values. But again, this is a variable value, so U being variable and lambda is variable, so if we can prove algebraically that this combination, maybe we'll say let A equal U plus lambda V of the set of V, because we're obviously just adding some combinations of vectors from real free, therefore this whole thing is going to be a V, which is just, maybe I'll just write that as well. Why not? Equals, I just think if you can name what kind of object it is in maths, because it's so quick to write that, you might as well, just so you don't get confused, you're very clear what this object is. This object is some element of V, and now what we're going to prove is that actually for all these combinations of lambda, U and V, this combination not only belongs to V, but furthermore belongs to U, and then we conclude our proof by lemma 3.6 as seen before. So, and the way we're going to do that is actually just going to expand out the algebra as the way to do it, which again seems ridiculous, but it's probably like the easiest, quickest, most convincing way to prove this result is simply to look directly at the algebra. So we can maybe write we see, or we could put furthermore, or to continue, or anything like that. No one really cares about the words. Just do some maths. So we've got A equals, as we discussed, ABC plus lambda lots of DEF. This suggests that A equals, we can combine, so we've got A plus lambda D, B plus lambda E, C plus lambda F. This is much less algebra than I thought it would be actually. It's quite interesting. Then we've got this. If A belongs to U, then x1, x2, x3. Oh. Maybe I'll draw it here. There are a number of ways you could do this. Maybe you could say let A equal x1, x2, x3 equal this thing, maybe here. So instead you could say A equals x1, x2, x3. And maybe you'd need to put the word, oh, we've got it here, let A equal. So maybe up here you should say let A equal. It's just how you want to lay it out clearly. I'm just trying to get a quick solution. You kind of see what a solution will look like. Not necessarily have a perfect solution, but just so you get the idea of how you go about solving this. But formalities wise, you could maybe do this, and then x1 and 2 and 3 are more logically like established, whereas here we kind of introduce them out of nowhere. But what I was going to do is write a note. This might be enough to get you marks, but you maybe don't want to risk it. Maybe you want to be more formal and add it up here. But anyway, in fact, you could probably get away with doing neither this nor that and be okay, just because x1, x2, x3 are generally known to be the free coordinates of A. But better not to risk it, you know. But you could write of A to be really clear as well. Of A. So if A belongs to U, then its coordinates satisfy this thing we put on our clipboard. It's a bit small, so we'll just expand it in a second. There we go. So we've got if A of U, then x1, x2, x3 of A satisfy this. Do they? Probably not the fullness way. But whatever, it's okay-ish. So in other words, because of what x1, x2, x3 are in the case of A, we've seen that these three values. So if it satisfies, we've got three lots of A plus, oh yeah, and this is the algebra I was talking about, you just get a quick bit of algebra to do, and you can conclude a result. So you've got minus 1 lots of B plus lambda E, plus to F equals 0. And now all we need to do is rearrange this until, oh yeah, we need to show that this equals 0. So it's not immediately obvious that this is true, we need to show it's true. And you probably shouldn't write a question mark, so I'll put it in brackets and remove it at the end. But just so you have an idea of what we're doing, we're trying to show these two sides are true. We don't know they are. Maybe we require versus we see. We require this, and then this simplifies 2. In general, the trick is we're going to try and squeeze out these exact terms, and if we can, we know these terms are 0, and therefore we can conclude that these two sides are the same. So to go about that, we probably just want to take the 3a, take the minus b, and take the 2c, and take the lambda d, 3 lambda d, sorry, the minus 1 lambda e, and take the 2 lambda f and combine. So we'll do that on the next step. If that wasn't clear, we're about to do it, so don't worry. So we've got the 3a from this bit. Oh, we should use colours here, that'll make it really, really clear actually. I generally want these to be more clear than more concise. The theory really is generally designed to be more concise. I'm okay with spending more time on this because this is for people who want to see a slower worked example. I can go a bit quick sometimes, sorry about that, it's just, you also don't want the video to drag on too long, you know. So we got, our goal is we're going to split it into these two things. Actually the minus 1 will multiply by both, but it's, you know what, it'll take 2 seconds. Be extra clear. So the 3 is going to go into the blue and the pink, and we're going to split off the blue terms and the pink terms is our goal. So, where's my pen gone? There it is. Okay, so we got 3a from the blue, we got minus b from that blue, and we got plus 2c from that blue in this bracket, and then we'll have whatever's going on over here. So we'll have 3 lambda d as our first pink term, and then we'll have minus lambda e as our next pink term, and then our plus 2cf as our final pink term. And I think that's fairly clear, so I'm not going to, no, I will. Just be. This is the only advantage of working with like a physical whiteboard or chalk, because it's much easier to switch colours on here, but we'll get there. So that's from the blue, that's from the pink. And then forget about the colours because all we care about is the actual algebra going on. For this next step, we're simply going to do, this is going to stay the same because it's already how we want it, which I'll show you in a second. And here we've got lambda lots of 3d minus e plus 2cf. So in order to conclude our results, we can already see it probably. Is remember we defined 3a minus b plus 2c to equal 0 and 3d minus e plus 2f to equal 0. So maybe label these so we can use them. So we'll call this maybe 3a, this 3b. So first of all we'll use 3a, which is that this thing equals 0. So therefore we have that 0 plus lambda 3d minus e plus 2cf. Why is there a c? That's just wrong. It should be lambda. That's why I'm getting really confused. I'm like, what the heck is that? Sorry about that. You're probably screaming at the screen being like, what is this guy doing? Aye. Slowly over time I'll get better at not making silly mistakes in maths presentation thingy me what's it's. Okay, we out here. Alright. Sorry, okay, so we got this, and we can say y by 3 points a, which was simply that thing was 0, so we can therefore substitute in 0. And then here we don't really need to say what we're doing here, but I'll explain it. So we got 3d minus e plus 2f equals 0 divided by lambda on both sides. Oh wait, we can't divide by lambda if it's 0. But if it equals 0, maybe you could, there's a small technicality here. You can probably get away with this though. No, even better. So we don't even have to deal with that rabbit hole of logic where we can't divide by lambda because it could be 0. We can just substitute in lambda multiplied by 0, which is justified by 3 point b, because we defined this thing to be 0 earlier. And therefore, we simply see 0 equals 0, which is true. We can remove this and give it a label. Call this 3 point C. So because this is true, we see, and we had both double arrows on every single point here. Let's see here. Therefore, this is true if and only if this is true, which is what we require to be true. Therefore, A satisfies this, and therefore A is the set of U. So let's just quickly write that as a formal conclusion. So this implies 3 point C is true. This implies that A belongs to U. And this implies that U subspace of V by lemma 3.6. And that's it. And what's crazy is, like, in the logical maths thing, you can actually write that in less words than I said out loud, and this is still like fine because of this handy little implies that symbol that you don't have when talking normally. So you can write your maths proofs sometimes quicker than you can convey your ideas using words, which is really cool. It's generally the idea of mathematics, I think, is to provide useful symbols that allow you to reason quicker than without them. So, yeah, the other idea I had was so ridiculous that I'll probably do it on my second channel. I won't do it here because it will just confuse people. But for people who are quick and sharp, they may have remembered that we put a little side note here, 3.*1, because I pointed out you really should just give a variable for each coordinate of U, different variable for each coordinate of V, and as you see, the algebra follows very nicely, very straightforward, you can't go wrong. But technically speaking, there's always more than one way to do things in maths, right? Same with engineering and a lot of science. Doesn't mean it's the correct way though. So I kind of noticed that we can actually make a substitution right on, and we can say, by the fact that we want this to be true, we can say b equals 3a plus 2c, and then for our start we can just say don't do this. You could technically do let u equals 3a plus 2c and equals c, and technically the only equation we need to hold now is, oh my gosh, does that just follow? Because whenever you shove this into there, it's true for a and c of the set of reals. So presumably when you do the algebra this way, I won't do it here, I'll link on my second channel if I did that. This is kind of exciting. It's also really stupid, but that's the kind of maths I like. So technically you can get away with having two variables here, but like why? Why would you do this? It's just painful and stupid. So don't do this, but you could. And I like spotting maverick ways to do things in unbelievably stupid ways because I think it's funny. Yeah, I have a kind of broken sense of humor. I get that. Okay, so yeah, don't do this. Forget this happened. Probably. Okay. But yeah, this is the good way to do it. Just have more variables. It's annoying to have 6 letters, but just do it that way, and you'll go less insane less quickly. You know. Okay. Well, that was some worked examples. Wow, this actually was longer than I thought it would be. But I don't see how you skip steps. This was even with me trying to skip a few steps in here and there. I guess this is just the amount of working required, as annoying as it is. Especially with these steps, like, you could probably see ahead in the algebra, but, I mean, technically, if you see ahead in the algebra, you just say, this is true here, and obviously that's not a formal way to do maths, so you kind of have to do the steps. I mean, different people argue about how many steps and how many you don't here. I generally think it's better to do slightly more and slightly less, but I can't imagine making the solution much shorter than this, if you're wondering about any of that kind of thing. Okay, well, thanks for hanging out with me, and I'll see you shortly again. Bye!